Did you know? I mean, oh,
Yes.
let me test the YouTube.
Mm-hmm.
Do you know? I mean.
So can I?
Yeah, no worry. Let's wait one more minute.
Okay. So can I change slides when you share the screen?
You know, I will give back to you. You know, after I finish the introduction, and
Okay.
then you can share screen.
Okay.
Okay, Marcin, let's start. Hello, good morning, good afternoon, and good evening. Welcome to the World River and Delta Source to Sink webinar series. So this series is co-sponsored by NSF, NC State University, Louisiana State University, State Key Lab of Ester and Coastal Research in Shanghai, and Utrecht in Netherlands. So today is November 23rd. Here is Thanksgiving holiday. Many people is travel on the road, but this is a recorded version of talk. And if you're not able to online, so you always can, but or your colleague or student can always go back our YouTube channel to watch the recorded version. So today we are great honor invite Professor Marcin Słowik from Adam Mickiewicz University of Poland come here talk about conditions to preserve sedimentary record of channel platform in temperate zone rivers. It's a kind of a global northern hemisphere overview or review. And before I introduce Marcin, and I would always a little bit background of this talk series. Since August 2020, we began this talk series. So far, we have already hosted 136 talks. All previous talks have been recorded, archived on our YouTube channel. As you can see here, you can just go to tinyurl.com/S2S talks. So as I mentioned, Professor Marcin Słowik, now assistant professor at the Institute of Geology at Mickiewicz University in Poland. Currently, he is a visiting Fulbright scholar in University of South Carolina. It's not too far from here. And he got his PhD in the same university, as you can see here, back 2004. His research is based on use geological, geophysical, and remote sensing method and sediment dating to reconstruct the evolution of meandering and breaching rivers in the past. The recent study is preferred to the river valleys situated in post-glacial and loess landscapes of Europe. And so now he's in US visiting scholar working on the river, Congaree River, South Carolina. So Marcin, now you can, I give the floor to you. You can share your screen.
Thank you very much. Okay, I'm sharing the screen. Okay,
yes,
let's start. Hello, everyone. Good morning, everyone. My name is Marcin Słowik, and as Paul said, I'm now in South Carolina, attempting to study the past of the Congaree River. However, the main topic of my today's talk will regard the preservation potentials of river valleys. I'm sure you know there are hundreds, if not thousands, of research works regarding past channel planform changes. And when we look at these research works, we can easily see that valleys situated even in the same geomorphic zone, even neighboring river valleys, differ significantly in preservation potential. Even in two neighboring river valleys, we can find a very well-preserved record of channel planform changes reaching back to thousands or even tens of thousands of years, while in a neighboring valley, this record is fragmentary. It is eroded and reworked by younger fluvial events. So here, together with my colleagues from University of Pécs, University of Łódź in Poland, and University of Szeged, we made an attempt to identify the conditions that are necessary to preserve a complete record of a channel planform that can be identified in the topmost part of floodplains. Here, I would like to underline that our work refers to the topmost layers of floodplains. So this refers to traces of channel planforms that can be seen in the floodplain's surface and in the topmost layers of the floodplain. So this is also how we define the term preservation potential. This refers to the topmost layer of the floodplain, and not to channel bodies or sedimentary structures preserved in I don't know, in ancient rock record. And by a complete record, we understand the record of channel planforms that maintains basic features of its geometry, such as channel width, thickness, and the channel section long enough to calculate sinuosity. So when we started this research work, we tried to define what variables may be responsible to define, may be necessary to define the set of conditions that we're trying that we are looking for. So we first thought that perhaps stream power, which indicates expenditure of energy by flow energy. So we made one of research tasks to estimate changes in stream power, also in geometry of paleochannels preserved in the floodplain record. The other thought was that perhaps space is needed to preserve sedimentary record of past fluvial events in river valleys. So we took valley width and channel belt width also as two important variables, and we determined relations. This was another research task, to determine the relations between valley width, channel belt width, and the age of paleochannels preserved in in river valleys. And you know, we have just finished our research grant, research project conducted in Poland and in Hungary. So we took this advantage and took our detailed field data, geophysical data from count penetrating radar, geological data from boreholes and corings, and radiocarbon and OSL datings to conduct a detailed analysis of changes of stream power, aggradation rates, also changes in channel belt width in two valleys, in the Shio Valley in Hungary and in the Middle Obra Valley in Poland. These two valleys represent exceptionally high preservation potential because the oldest channels, paleo channels found in the Obra Valley are 15,000 years old. And in the Shio Valley, they are at least 18,000 years old. So this we had two really good examples to study the conditions influencing the high preservation potentials. Beside these two detailed study sites, we have conducted a literature review, and we searched in the literature for data regarding stream power, paleo discharges. We looked for publications with geological cross sections that may have outlines of paleo channels. This would make possible to calculate, to estimate paleo discharges, also values of stream power, and also we looked for publications with available results of sediment dating, radiocarbon dating, OSL dating. This would provide us the age of paleo channels. And we were able to find the information about 20 rivers. These rivers represent most of all post-glacial landscapes of Europe, also less landscapes of South Central Europe. But we have found also some very detailed studies regarding the evolution of rivers, high energy rivers situated in mountainous settings, such as the Pariamento River, like South Saskatchewan River. So we have found data for a variety of rivers, of meandering rivers, anabranching rivers, low energy anastomizing rivers. So we took the data from the presented literature for the analysis of channel platform changes. When in cases when part of the data was missing, like paleo discharges, stream power, and we tried to estimate the paleo discharges and stream power from based on geological cross sections where outlines of the channels were presented. And part of missing data, like channel belt width, was if it was missing in the literature, it was measured from on Google Earth using distance measurement tool. So beside the literature review, we have determined elements of channel geometry such as sinuosity and braided indices, and also valley width to channel belt width ratio, because we thought that channel belt width itself may not be sufficient variable to determine the preservation potential. As I said, we have also estimated stream power for all the identified generations of paleo meanders, paleo channels, paleo meanders. And this is, of course, estimation. We all know that estimations of bankful discharge, as well as the estimations of stream power, bear very large uncertainties. This comes from calculations of wetted perimeter, from cross-sectional area, and of course from the estimations of Manning roughness coefficients. So these uncertainties are large in case of large flow, for example, for large-scale meanders. The standard errors covers here at least 50% of the estimated discharge, and almost 40% of estimated discharge for small-scale channels, for smaller magnitude paleo discharges. So here I would like to say that the estimated stream power must be treated here as showing general trends, not like showing precise values of stream power, but sets of stream power can show us just general trends of changes. So this is why the findings from the changes in stream power were supported with plots of the age of former channels and valley with channel belt width ratio. Here, as you can see, we used GPR, ground penetrating radar images, in cases when it was possible to identify the outline of the channel, outlines of the channels of paleo channels on the GPR images. We used these images to determine wetted perimeter, cross-sectional area, and bankful width, and this was then used to estimate bankful paleo discharges. Okay, so what are our results? What are our findings? We have identified 4 groups of rivers differing in preservation potential. The first group are low energy meandering and ana-branching rivers characterized by a successive decrease of stream power and channel belt width. And when we look at the trends of stream power, we can see that in the late pleniglacial, in the late glacial, so in period between 18 and 12,000 years before presence, the values of stream power were relatively high, but then they successively decreased in particular rivers. These are rivers. Here you can see examples of rivers of Central and South Central Europe. This is the Varta River. That shows very nice examples of preservations of at least 2 generations of paleo channels. Large-scale paleo meanders from the late glacial situated along the edge of the valley, and the smaller scale meanders active in the Holocene situated closer to the center of the valley floor. So, so in particular, in successive generations of paleo channels, stream power successively decreased, and this trend was present until the late Holocene, till the period of the last 3,000–4,000 years, where this decreasing trend was stopped or even reversed in some cases. Now, let's look what happened to valley with channel belt with ratios. We can see that in most studied rivers of this group, the ratios successively increase. This means that the width of the channel belts successively smaller, providing that the valley width was constant through all the time. And most of the valley width channel belt width ratio amount to between 6 and 12 in most valleys. So this is possibly a suitable indicator for someone who plans research aiming to investigate the evolution of river planforms in the past, to take into account valleys with valley to channel belt width ratio between 6 and 12, and preservation of at least 2 channel planforms in the valley floor. So here you can see that both the Prosna River have traces of at least 2 former channel planforms, Varta River, and also Tisza River, the major river in Hungary, one of major rivers in Hungary that flows through the Great Hungarian Plain. Now let's take a look on the second of the distinguished group of rivers, These are low energy meandering and anastomizing rivers with constant width of channel belts and degrading conditions. So here you can see that the trends in the changes of stream power are completely different from the previous group of rivers. Here we can see two very unique examples of fantastic anastomizing low energy rivers, the Upper Columbia River in British Columbia, Canada, and Middle Narew River in Poland, in eastern part of Poland. So when we look at the stream power changes in paleochannels of these rivers, we can see that in general the values are low, but there are periods of increase of the stream power here in the Narew River about 2,000 years before present, and here you can see changes in the Upper Columbia River about 3,000 years before present and about 1,000 years before present. Here, I would like to say it's very tempting to say that this temporal increase of stream power might have influenced the formation of avulsions in these river courses. As we know, anastomizing rivers evolve through avulsions. So it's tempting to draw such a conclusion. However, we must be cautious with it because these are low energy rivers. So the formation of avulsions takes time in this river system in centennial time scales. It needs centuries to form a new river course by avulsions. This river system. So this is just a suggestion. So there are also low energy meandering rivers in this group of rivers. These are rivers like the Kaposh and Kopan rivers evolving in less landscape of Transdanubia. Transdanubia is a beautiful region of Hungary comprising of sets of hills built of less. And so Kaposh and Kopan river, Lower Obra River in western Poland, also low energy sinus rivers like Drenthe and Overijsselse Vecht in the Netherlands are examples of low energy meandering and sinus river maintaining low stream powers in millennial timescales. So the average age of paleochannels preserved by both the anastomizing and low energy meandering rivers valleys is between 4,000 and 7,000 years before present. And as you can see, the valley to channel belt width ratio, the value of the ratios are close to one. So these rivers occupy close to the whole. They are very close to occupy the whole width of the valley. But these are low energy systems, so they can all the same they can preserve the record of channel planforms in millennial timescales. Now let's move to more energetic river systems. There are moderated high energy meandering rivers with constant channel belt width and intensive lateral migration. And these are very well-known examples of Bollin and Dane River in England, Allier River in France. They migrate intensively. The migration rates are counted here counted in meters per year. So the ancient sedimentary record is eroded and reworked by the modern riverbed. There are examples of let's call it paleochannels, both in the Bollin River and Allier River, but they were cut off from the modern riverbed in the 19th century. And there is also a very unique example of Wear River in the United Kingdom, high energy ana-branching river. And so the highest the lowest preservation potential, is represented by a group of high energy braided rivers reworking the whole valley width. And here, this we can see here impressive examples of high energy braided rivers like Paliamento River, Kicking Horse River in Canada, Sagavanirktok River in the northern slope of Alaska. So these rivers rework the whole width of the channel belt every few years. So here the preservation potential may be counted in a maximum decadal time scale. And sometimes this is annual time scales. So the valley to channel belt width ratios are close to 1, and there are very high flow energies of the modern rivers, and the preservation potential is very, very small here. So these are the 4 groups of rivers. Now let's take a look what happens if we take to determine the preservation potential only valley width. Here we have plotted the values of the valley widths with the maximum age of channel planforms preserved in the floodplains. So at first sight, we have a very nice differentiation here. The group of rivers with the highest preservation potential is situated away from the other group of rivers. Also, the anastomizing and low energy meandering rivers are situated well, separate from the high energy rivers. However, when we look at a range of the valley width, except especially between 1 and 3 kilometers, 3 kilometers wide valleys, we can see that in this range of valley width, we can find a variety of rivers with completely different preservation potentials. We have here high energy braided rivers. We can find here as well the unique examples of low energy anastomizing rivers like Narew and Upper Columbia, and preserving the record of channel planforms between 4 and 5,000 years before present, maximum age, and also the Shio Valley, when we can find several generations of paleochannels, and the oldest ones are about 18,000 years old. So valley width itself, it's not sufficient indicator to determine the preservation potential. Now I would like to tell you a few more facts about our studies conducted in the Middle Obra and Shio valleys. As I said, these 2 examples are very exceptional examples of rivers containing very high preservation potential, containing several generations of paleochannels. The Obra River is situated in the western part of Poland, and its middle course is situated in the Warsaw-Belin Proglacial stream valley, in other words, ice marginal valleys, that was formed by melt-out water of the last inland ice. So the valley conveyed huge volumes of flow to the west, then to the northwest, to the North Sea. And here we have studied a fantastic example of former multi-channel connection between the Obra Valley and the Odra Valley, 2 very similar names. Odra is a major river on Polish on the border between Poland and Germany, and we have studied the Middle Obra River. So this multi-channel delta-like connection was active. It was active until the turn of the 18th and 19th century. So last remains of multi-channel flow were stopped here by intensive hydrotechnical works. But here a great variety of fluvial landforms were preserved. like starting from large-scale meanders, active about 15,000 years ago, small-scale meanders active in the Holocene, and also sinus channels and ana-branching channels active in the Holocene until the major hydrotechnical works conducted in this area. This is how the river valley looks today. Here you can see fantastic traces of large-scale meanders situated along the margins of the valley, and there are also remains of an ana-branching planform active. It was active throughout the Holocene until the end of the 18th century, and now here you have artificial canals, and well, only single paleo channels belonging to the former ana-branching system are preserved today. They are marked by belts of trees. These are actually belts of older trees. Now let's take a look on the Shio Valley. This is situated of the region of Transdanubia. This is southwestern Hungary. And this is also a fantastic example of preservation of here at least 3 generations of paleochannels, starting from large-scale meanders active about 18,000 years ago, through traces of an ana-branching pattern active from 18 to about 13,000 years before present, and finally remains of scale meanders active throughout the Holocene. And here you can see pictures of the large-scale meander situated along the edge of the valley. The outer part of the former meander is slightly elevated because these are slope deposits delivered from the eroded valley slopes. So we conducted major fieldwork, collecting sediment samples for grain size analysis and sediment dating from this part of this huge paleo channels to make sure that we are investigating an alluvial fill. So the width of this huge channel is about 200 meters. So these are really impressive fluvial landforms. If you would like to get more information as well as our data, you are welcome to read our 2 recent publications, one published in Global and Planetary Change, and the other one in Catena. So now let's look how the trends in changes of stream power and channel valley width to channel belt with ratio changed through time in both studied valleys. Here you can see 2 schematic cross sections, geological cross sections, that also show some general trends in dimensions of the channels. So both river systems evolving from large-scale meandering channels to smaller scale ana-branching and meandering systems. Also crevasse channels were formed in the middle Obra Valley. We have also calculated here values of aggradation rates. This must be said that the aggradation rates refer to the channel hills, because we have most data we had sediment dating data originated from the channel fields. So when we look at the potential specific stream power, in both cases the stream power successively decreased until the last about 3,000 years, when these trends were reversed. There was a temporal increase of stream power in both river valleys. Why did it happen? This happened because of a coupled influence of climate changes and human impact. The climate in the late Holocene, during the last 3,000–4,000 years in Central Europe, became more humid. There was increase of precipitation. You can see here that flooding phases occurred both in the Vistula Valley and the Tisa Valley at that time. These are neighboring valleys, we can say, to the Shio and Middle Obra River. Precipitation increased in West Central Europe, and also humans appeared in these areas. The first traces of human appearance on both areas, I mean here the Middle Obra and Shio Valley, took place about 7,000 years before present, and this present became successively more and more intensive, we could say. So humans cut forest. There was successively increased deforestation. They burned vegetation to make space for agriculture, for pastures. So when the deforestation proceeded, the runoff from slopes was increased, and slope erosion was also increased. As a result, we can see that the aggradation rates both in the Middle Obra and Shio valleys are higher than in the Middle Holocene or in the early Holocene. These aggradation rates are significantly higher. So these events in connections with increased flood frequency and climate humidity and precipitation could have influenced the temporal increase of stream power in this period. But this increase of this stream power was not strong enough, was not high enough to erode and rework this ancient channel record. There is another very interesting thing here regarding valley to channel belt width ratio, because as you can see in the Shio Valley, this ratio successively increases. This shows that the channel belts in the Shio Valley successively decreased, but the behavior of this ratio in the Middle Obra Valley is completely different. We have a significant increase of the ratio, and then the value remains more or less the same, and the values were really high. It starts with about 8 or even 9 in the Middle Obra Valley. This means that the large-scale meanders did not occupy the whole valley width. So let's take a look at this map again. And here, I would like to say that, I would like to repeat that the Middle Obra Valley inherited its valley, its location from the ice marginal valley, the Warsaw-Berlin ice marginal valley formed fluvioglacial flows. So significant part of these valleys are covered by fluvioglacial sediments, fragments of outwash plains. There are also sets of small dunes formed in the late glacial in this area. So this is why, from the beginning, the fluvial processes formed only part of this huge valley inherited from fluvioglacial flows. So this is why these changes of valley to channel belt width ratio are so specific. Yes, and one more thing I would like to say is that the aggradation could have been caused by human presence and increase of sediment delivery from slopes, but also from sea level rise. The sea level both of the Black Sea and the Baltic Sea were relatively high compared to the middle or early Holocene. Okay, now I would like to discuss a bit a possibility to extend the presenting framework of rivers with various preservation potential by examples of rivers preserved in the rock record. We have made an attempt to track the trends in stream power also in I don't know how to say, vertical look, because this approach, as you can see, is a horizontal approach. We look how the channels, the stream power of channel changed horizontally from large scale meanders close to the edge of the valley until the smaller scale anabranching and meandering rivers in central part of the valley. So here we also found decreasing trend of stream powers in vertical sedimentary record. But this refers only to the part of studied rivers. The main condition is that a high energy river system should be replaced by a lower energy river system. This was the case of the Middle Obra, Shio, Varta, Tisa River, where high energy braided systems were replaced by a relatively lower energy meandering systems. Of course, after these transitions, part of the sedimentary record belonged to the braided rivers were reworked. However, still a significant part of the fluvial record is preserved. Similar situations regards anastomizing rivers or even sinuous rivers evolving through oblique aggradation, such as the Drenthe River in the Netherlands, where in these areas also high energy braided rivers were replaced by low energy aggrading anastomizing systems. So here it is possible that perhaps the decreasing trends in stream power might be a good indicators of preservation potential only also in not only in the surface floodplain layer, but also in deeper sedimentary layers, even in rock record. However, one important thing must be remembered here, that channel bodies in the rock records as well as sedimentary structures undergo compaction. So the real shapes of channel bodies may be here. May be very difficult to reconstruct. So these are the main conclusions of my talk. The successive decrease in stream power accompanied by increase of valley to channel belt width ratio may be treated as indicators of sedimentary indicators of high preservation potential in millennial or multimillennial timescales. Low energy meandering and anastomizing rivers preserved the record of channels stretching back to between 4,000 and 7,000 years ago. The periods of increased stream power that we identified here might be used as indicators of avulsions. However, this must be treated with caution. This matter should be further investigated. There are also high energy rivers reworking the fluvial records in centennial or even decadal timescales. Perhaps good information for people who would like to study the past of the rivers, the evolution of rivers in the past with the valley to channel belt width ratio between 6 and 12 and traces of at least 2 generations of paleomeanders may indicate areas with high preservation potential. And this framework that we proposed here may be extended by more examples, like from mega rivers, and it might be in the future extended by examples of fluvial records preserved in the rock records. Thank you very much for your attention. This talk is part of contains information from our publication that was from our paper that was published this year in Journal of Geophysical Research, Earth Surface. So there in this paper you will find more detailed information as well as detailed data sets that we used for our analysis. Thank you very much for your attention.
Oh, thank you, Marcin, for this great talk. And, you know, I definitely learned a lot about the meandered channel and with timing and the width, the relationship, and the deposition record. That's great. Okay, our audience, if you have any question now, you can just unmute yourself and directly ask Marcin. Yeah, go ahead.
Hello, Marcin, again. Thank you for the talk. And one thing which is really interesting for me is if the preservation of the forms which you analyzed is correlated to the preservation of the sediments, of the deposits left, for instance, by particular floods and so on. Have you also tried to compare the depositional record in the same context?
Yes, in my we have both here preservation of forms, of fluvial forms, and depositional record, because this paleo channel is preserved in the topmost layer of the floodplains. They do preserve sedimentary record containing sedimentary structures like traces of oblique aggradation, marking the lateral migration of the channels. So this reconstruction, in my opinion, this framework also refers to the positional record. Of course, it may be here an extension may be needed here by putting more attention to sorts of sediments constituting alluvial fill, sorts of sediments constituting valley floor, and sorting out types of sedimentary structures in particular group of rivers. So yes, in this direction it may be developed, of course. I don't know if I answered your question.
Thank you.
Marcin, you know, many your case study is a relatively kind of small river, or sometimes as a mountain glacial faded river. So you also mentioned the potential for the large river. What, you know, in a large river, you know, system like Mississippi River, you know, what you're concluding how to apply, you know, we can for this kind of large, because large river relatively the channel stable and you know, maintain all year flow, you know.
Well, this is regarding large rivers, mega rivers, like the Amazon River, like the Mississippi River. The task is really complex because maybe not all, but significant part of mega rivers develop in cratonic basins, in cratonic settings. So I'm aware of publications of John Jansen, for example, from the Cooper Creek Basin. And they show that the present huge system of Cooper Creek reworks only the surface layer of a huge basin. So this basin, like Cooper Creek, like the Amazon, like I'm sure the Mississippi River, must contain several layers in vertical record of successive generations of channels. Here it's a challenge. It would be tempting to try to study these river systems by using geophysical methods, maybe seismic methods, to retrace the geometry of former channel bodies, and in this way investigate changes in river planforms in really multi-millennial time scales. But still, we still have this problem that these channel bodies undergo compactions after being covered by the next sediment layer. But we already know from the publications of Janssen, from publications of Edgardo Latrubese, that this record may reach at least 50, 60,000 years before present, at least.
Okay. Sometimes, how about the event? For example, the big ice lake bust, the ice dam collapse, that kind of event, 100-year scale or 1,000-year scale event, impact the channel migration of the width or depths.
Oh yes, there are fantastic examples of such glacial outbursts. There is a fantastic research work from the area of Poland, Eastern Poland, published in Earth Science Reviews by Piotr Wegwert and co-authors. Yes, so this is another. Although this is more, for me, this is more fluvioglacial event, not fluvial event, but such events may have been responsible for the formation of several landforms, such as ice marginal valleys in the areas of Europe. So yes, extending the framework to these landforms, and then finding to what degree this records of huge events is eroded then by fluvial activity, which would also be very interesting.
Yeah. Okay. How about any other? Audience? Any comments, question, suggestion? Okay. Okay, we see Carl is here. Carl, how are you? Haven't seen you for a while. Still here.
Yeah, I don't know.
Okay. Okay. If
Okay.
Yes, I'm here.
Carl, how are you?
Hello, Carl. How are you?
Hey, Marcin. How are you doing?
Fine. Okay. I'm settled and started field research in the Congaree River.
Good.
So far, so good. Thank you.
Okay.
Fine.
It's okay. How are you? Everything
Oh,
okay?
it's okay. I'm just in the final stage in preparing an opus proposal.
Okay.
Deadline is approaching, and so we are busy.
All right. I keep my fingers crossed that you succeed, Carl.
So good luck for your research.
Thank you.
Okay.
Thank you
So,
much.
Marcin, we're looking forward, to your update about the local Congaree River, South Carolina. See.
Yes, sure.
Okay. So, if no any other question, and I thank you very much. And so, this year, I think this is the last Source to Think talk this year. So, December. We have some schedule issues, so we haven't figured out. Some speakers want to maybe postpone to the earlier next year. Then we will see. Keep tuned. We will keep you informed. Okay. Otherwise, thank you, Marcin. Thank you, everybody. I know it's Thanksgiving here. Many people is out of town, and so but It's
Okay.
great. Okay.
Thank you.
Okay,
Thank you.
enjoy
Bye-bye.
Thanksgiving.
Yeah.
Bye-bye. Bye.
Thank you.
Okay. Bye bye.
Thank you very much.